This webcast continues a discussion of how to solve problems that involve unbalanced forces, or in other words, how to solve problems that involve Newton's second law. And before we continue to the later problems in Worksheet 5B, let's recall the strategy that we've been using. The first thing that we need to do is to write two different equations to solve for the net force. One of them is Newton's second law, which says that the net force equals the mass multiplied by the acceleration. The second equation, you will look at your force diagram and you will add the forces parallel to the direction of motion. And although I've put the most common in the problems we've been looking at equation, note that this equation is going to depend on the specific situation that you're looking at, okay? And then once you have these two equations to find net force, then you're going to set them equal to each other, and then you will solve for the variable that you're trying to find. Okay, so let's go over to Worksheet 5B and continue with some of these problems. So the first one is number 8 in this worksheet, and here we're talking about a grocery bag, and the bag will rip if it applies a force of bigger than 250 newtons. And so we're supposing that this bag is filled with 20 kilograms of groceries, and then it gets lifted with an acceleration of 5 meters per second squared. And we're trying to decide, does the bag rip or doesn't it? And so let's look at the forces on the groceries. The reason I want to look at the groceries is because I know that the bag is supporting the groceries with a normal force, right? And that's the force I'm going to look at to see, is that bigger than 250 newtons or isn't it? Okay, so here is my force diagram. I'm thinking about the groceries. Good place to start is the weight of those groceries, right? The weight is the gravitational force being exerted on the groceries by the Earth. And since the groceries have a mass of 20 kilograms, I'm going to multiply that 20 by 9.8 to get that weight. And I get 196 newtons, okay? So that is the force pulling the groceries down. The bag is exerting a force that supports the groceries, and in this case we'll be lifting them up. And that's a normal force. It's being exerted on the groceries by the bag. Okay, I don't know what that is yet. I know that the maximum it can be is 250 newtons. Okay, so I'm going to use the strategy we've talked about. I'm going to write two different equations to find the net force, and then I'm going to set those two equations equal to each other. Okay, so the first equation is using Newton's second law, that the net force equals the mass times the acceleration. Well, I happen to know both of those quantities. I know that the mass of the groceries is 20 kilograms. I know that the acceleration, they're telling me, is 5 meters per second squared. And so the net force on the groceries must be 100 newtons. Okay, that's one of my equations. The other equation is going to be one that I use based on this force diagram. So when I look at the force diagram for this situation, to find the net force in the vertical direction, that's the direction of motion, I add the normal force because it points up, and I subtract the gravitational force because it points down. Okay, I know the gravitational force. I do not know the net force. That's okay. I'm not going to worry about, the normal force. I'm going to wait for a minute on that. Now I'm going to set these two equations equal to each other because they're both telling me how to calculate net force. One of them is MA. The other is the normal force minus the gravitational force. The thing that I'm solving for here is the normal force. If that force is bigger than 250 newtons, then the bag rips. Okay, so I've already calculated MA, that equals 100. I don't know the normal force yet, but I know that the gravitational force is 196. So to solve for the normal force, I'm going to add the 196 to both sides, and I see that the normal force must be 296 newtons. Well, that is larger than 250 newtons, and so that must mean the bag will rip. If you try to lift the groceries up at an acceleration of 5 meters per second squared, it's going to take such a large force that it's going to cause the bag to rip. Okay, let's go on to number 9. Here we have an elevator, and it says that the maximum occupancy is 25 persons. And it tells me that the safety engineers assume the mass of the average rider is 70 kilograms. Therefore, the maximum mass of the passengers should be 25 multiplied by 70 kilograms. And let's see what that is. That's 1750 kilograms. And then the mass of the elevator itself, they give us as 560 kilograms. And therefore, the total mass that gets accelerated is going to be the combination of those two. So it'll be the 1750 plus the 560, which is 2310 kilograms. Okay. Okay, the problem goes on to tell us that the cable that supports the elevator can only tolerate a maximum force of 34,000 newtons. Okay, let's do a force diagram for the elevator. Okay, so I'm going to start with the weight of the elevator itself. That's the gravitational force on the elevator that's being exerted by the Earth. And that's going to be the mass of the elevator, 560 kilograms, multiplied by 9.8. And so that is 5488 newtons. That's the weight of the elevator. Now the passengers are standing on the floor of the elevator, and so their weight is pushing down on the elevator. That's a normal force. It's being exerted on the elevator by the passengers. And that force, it is a normal force, but it equals the weight of the passengers, right? And we said their total mass is 1750 kilograms. And so I have to multiply that mass by 9.8. And so that's going to be 17,150 newtons. Okay, so those two forces are pulling the elevator down. The cable supports the elevator and holds it up. And since it's a cable, that force is a tension force. It's on the elevator and it's being exerted by the cable. Now, I don't really know. I guess I know that the maximum amount of this tension force is 34,000 newtons. Okay. And so my question is, what is the greatest acceleration that the motor can produce without snapping the cable? Okay, so it can cause a tension force of 34,000 newtons at the maximum, and that's going to give us the maximum acceleration. Okay, my strategy is I write two equations to calculate the net force, and then I set those equations equal to each other. Okay, so the first equation is going to use Newton's second law. That tells me the net force is the mass that accelerates multiplied by the acceleration. Well, I know that the mass that accelerates is 2310 kilograms. I mean, we calculated that up above, right? I don't know the acceleration yet. Okay, I'll just leave it as A. The other equation, I'm going to look at my force diagram and add those. I've got three forces. I have to add them to find the sum of all the forces on the elevator. So I add the tension force because it points up. But then I'm going to subtract both the normal force and the gravitational force because they both pull down. I have values for all of those forces, and so I might as well go ahead and plug those in. I've got 34,000 minus 17,150 minus 5488. And so the net force, I know, is 34,000 minus 17,150 minus 5488 is 26,802 newtons. Okay, now I set these two equations equal to each other. So my first equation is 2310 times acceleration. My second equation, I've already calculated that. It's 26,802. And so the acceleration, I just, divide both sides by 2310. And I have a math error here. Let me go back. I'm so sorry. This 34,000 minus 17,150 minus 5488 is actually 11,362 newtons. So I had a fat finger in my calculator. So let me replace this value. And I'm going to divide that by the 2310 kilograms, which is the total mass of the elevator plus the passengers, right? Because they're both accelerating. And then I get that the acceleration, the maximum acceleration, is 4.919 meters per second squared. Okay, let's go on to number 10. This is about a helicopter. This is an interesting problem. So it tells me that a helicopter that has a mass of 5,175 kilograms can accelerate a 13,000 Newton load of cargo upward at 2.2 meters per second squared. So let's think about the force diagram of this helicopter. You could think of the helicopter as being like a elevator for that cargo, right? There are boxes of stuff sitting on the floor of the elevator, of the helicopter. Okay, so I'm going to start by putting the weight of the helicopter itself. And I'm just going to abbreviate helicopter to heli. But that's a force that the Earth is exerting on the helicopter. And I can calculate that by taking the mass, 5,175 kilograms, and multiplying by 9.8. And I get 50,715 newtons. Okay? That cargo is sitting on the floor of the helicopter, and so that's exerting a normal force. And this is by the cargo. And I don't have to calculate that, right? They already give that to me as a force because it's in newtons. So I don't multiply it by 9.8, right? I keep that as 13,000 newtons. And then the force that causes the helicopter to move up in the air is, we're going to call it a lifting force. And it's being exerted on the helicopter by the engines. Okay, I don't know what that is yet. Okay, so let's see here. So we want to find the net force on the helicopter, but we also want to find the lifting force of the helicopter. We want to find both of those forces. And remember, I might answer these in different order, but I'm going to use the strategy we've been talking about, which is that I write two different equations to solve for the net force, and then I subtract, or I set those two things equal to each other. Okay, so one of those equations for net force is Newton's second law, which is net force equals the mass multiplied by the acceleration. Okay, they told me the acceleration, but do I know the total mass that's accelerating? I might need to calculate that. So I know that the helicopter is part of that mass, right? So I know that the helicopter itself has a mass of 5175 kilograms. Do I know the mass of the cargo? Not yet. I know the weight of the cargo. I'm going to have to calculate its mass. So I take its weight, 13,000 newtons, and I divide by 9.8. So the mass of that cargo is 1326. Actually, I'm just going to round it to 1327 kilograms. So then the total mass, I add those two things up, 5175 plus the 1327, and I get 6502 kilograms. Okay, so now I am able to calculate the net force. Let's see. I'm going to move this stuff up just a little bit. Okay, and that way I can just continue writing here. The net force is that total mass, 6502 kilograms. And they've given me in the problem the acceleration. It's 2.2 meters per second squared. And so when I multiply those two things together, I get that the net force is 14,304.4 newtons. That is one of the questions. That's the net force on the calculator, on the helicopter. Okay, but to solve this problem, I also need to write another equation to find the net force. And this is the equation that I find by looking at the force diagram. And here I've got three forces, and so I have to write the equation for how I add those together. I add the lifting force because it points up, but I subtract the normal force and I subtract the gravitational force. Okay, I know two of these. I do not know the lifting force, so I keep that just as a variable, but I know that I have to subtract the 13,000 and I have to subtract the 5715. Now I set these things equal, okay? So my first equation I solved, and it's just 14,304.4. That's the net force, and that equals the lifting force minus 13,000 minus 5715. And so when I solve for the lifting force, I get 78,019.4 newtons. And so that's the answer for part C here. It's 78,019.4 newtons. Okay. Well, then the last part of this question says, okay, a crewman has put so much cargo in the helicopter that it can't lift off the ground. If it really can't lift all off the ground, it's stationary, right? It's not moving. And that tells me that the net force on the helicopter must be 0. So in other words, the net force, which is the lifting force minus the normal force minus the gravitational force, must be 0. The lifting force is unchanged, right? The ability of the engine to lift the helicopter doesn't depend on how much cargo you put in the helicopter. The weight of the helicopter itself is unchanged, right? The mass of the helicopter has not changed. But the weight of the cargo has changed, right? Because the amount of cargo, the mass of the cargo has changed. So that's what I'm going to be solving for. Okay, so let's see here. I know that the net force is 78,019.4 newtons. That hasn't changed. That's the lifting force. Minus the normal force is the mass of the cargo multiplied by 9.8, right? That's how I would find that normal force. It's the weight of the cargo. So it's its mass times 9.8. And the weight of the helicopter itself is still 50,715 newtons. And all of that equals 0. So now I'm going to solve for the mass of the cargo. So let's see. First, I need to move everything, or actually, you know what I can do? Instead of doing that, I'm going to add the mass of the cargo times 9.8 to both sides. Okay, so then I have 78,019.4 minus 50,715. On this side, I have 27,304.4. And then on the other side, I have the mass of the cargo multiplied by 9.8. So now I divide both sides by 9.8, and that's going to give me the mass of the cargo. And it's 2,786.2 kilograms. Okay. And let's look at one more, number 11. Here we have an engine pushing a large SUV to the right with a force of 5,000 newtons. And we've got friction, and we've also got a drag force. Okay, so let's do a force diagram for the SUV. Okay, so the engine is pushing it to the right. So this, we can call it an applied force on the SUV by the engine. And they're giving us the amount of that. It's 5,000 newtons. There's a friction force that opposes the motion. That's acting on the SUV, and it's by the road. They're telling us that the friction force is 3,800 newtons. There's also a drag force. Drag force is also opposing the motion, right? This is a drag force exerted on the SUV by the air that it's running into, and that's 900 newtons. Let's see. Oh, the weight of the SUV, that's the gravitational force being exerted by the Earth, and that's going to be 1,000 kilograms. That's the mass of the SUV times 9.8, so that's 9,800 newtons. And then there's a normal force. You know, the SUV is not falling through the road. The road supports the SUV. And since there are only two forces in the vertical direction, the net force in the vertical direction must be the normal force minus the gravitational force. And in this case, it's going to be 0, right? Because the SUV is not moving in the vertical direction. When something's not moving in that direction, the net force in that direction is 0. So therefore, the normal force must equal the gravitational force. And so it must also be 9,800 newtons. Okay. I could put congruency marks to show that those two vertical forces are equal to each other. Then it says let's write an equation to find the net force in the horizontal direction. That's the direction of motion, right? Okay, so I add the force that goes to the right, which is the applied force, and then I subtract the forces that go to the left, the friction force and the drag force. Is the net force in that direction 0? I don't know. They haven't really told me that it's moving at a constant velocity, but I have values for all three of these forces, and so let me plug those values in. I've got 5,000 minus 3,800 minus 900. Let's see what that is. I get 300 newtons, so it's not equal to 0. So that must mean that that there is some acceleration of this SUV. So since the net force is to the right, there's more force to the right than there is to the left, that means it's accelerating to the right. And since the velocity is also to the right, that means that it is speeding up, right? Velocity and acceleration are in the same direction, so it's speeding up as it moves to the right. And so let's find the amount of the acceleration. Well, I know that the net force equals the mass times acceleration, right? That's Newton's second law. I need to solve for acceleration, so I'm going to divide both sides by mass. And so the acceleration is going to be the net force divided by the mass, which is 300 newtons, divided by the 1,000 kilograms. And so that is 0.3 meters per second squared. That's a 3.